Welcome to this coding walkthrough on LeetCode problem number 2078, two furthest houses with different colors. In this session, we'll break down the problem, explore the brute force approach, and understand the key concepts behind solving it. Let's dive in. In this problem, we are working with an array called colors, where each element represents the color of a specific house in a row. The task is to find the maximum distance between two houses that have different colors. The distance between two houses is defined as the absolute difference between their indices in the array. For example, the distance between the house at index 2 and the house at index 5 would simply be a 2, 5, which equals 3. The output of the problem is an integer representing this maximum distance. The input array colors has a length of n, where each element is a non-negative integer, and it is guaranteed that there will always be at least two houses with different colors. This ensures that the problem is well defined, and no edge cases like all houses being the same color need to be handled. Now, let's look at some examples to better understand how this works in practice. Here's our first example. The input array colors is 1, 1, 1, 6, 1, 1, 1. In this case, the house at index 3 has the color 6, which is different from the color of the house at index 0, which is 1. The distance between these two houses is calculated as a 3 is 0, which equals 3. Similarly, the house at index 3 also has a different color compared to the house at index 6, but the distance is the same, 6, 3 equals 3. Since there is no pair of houses with different colors that has a distance greater than 3, the output for this example is 3. Now, let's explore another example with a different array of colors. In this second example, the input array is colors equals 1, 8, 3, 8, 3. Here, the house at index 0 has the color 1, and the house at index 4 has the color 3. These colors are different, and the distance between these two houses is 4 is 0, which equals 4. This is the maximum distance between two houses with different colors in this array. Notice that while there are other pairs of houses with different colors, none of them have a distance larger than 4. Therefore, the output for this example is 4. Let's now consider one final example to solidify our understanding. For the third example, the input array is colors equals 0, 1. There are only two houses in this array, and they have different colors. The first house has the color 0, and the second house has the color 1. The distance between them is 1 is 0, which equals 1. Since there are no other houses in the array, this is both the maximum and the only possible distance. The output in this case is 1. To summarize, the problem guarantees that there will always be at least two houses with different colors, and the constraints ensure that the input size is small enough to allow solutions with quadratic or linear time complexity. This makes the problem approachable while still leaving room for optimization with more efficient algorithms. To solve this problem, one approach we could consider is the brute force method. The intuition here is straightforward. We test every possible pair of houses and calculate the distance between them if their colors are different. Specifically, for each house at index I, we compare it with every house at a later index j, checking if their colors differ. If they do, we compute the distance j, I and keep track of the largest distance we find. The algorithm involves two nested loops to generate all pairs, I, j, where I less than j. For each pair, we check the color condition and update the maximum distance if needed. While this approach is simple to understand and implement, its major downside is the time complexity of n squared. This quadratic growth makes the method impractical for larger arrays, especially when the input size approaches 10,000. However, it does not require extra space, as the space complexity remains 1. The brute force approach has clear limitations. It involves redundant checks and becomes computationally expensive as the input size grows. For instance, if we have an array with a length close to 10,000, the number of pairwise comparisons would be around 50 million, which is highly inefficient. To address this, we can turn to an optimized approach that leverages the structure of the array. The key insight is that the maximum distance between two houses with different colors can often be determined by focusing on the endpoints of the array. Specifically, we look at the leftmost house and the rightmost house as potential anchors. If the leftmost house has a different color from any house on its right, the farthest such house determines one possible maximum distance. Similarly, if the rightmost house has a different color from any house on its left, the farthest such house determines another potential maximum distance. This observation allows us to shift away from checking every pair to focusing only on the relevant extremes, significantly improving efficiency. The optimized approach can be implemented efficiently in linear time. First, we start by scanning from the leftmost house to find the farthest house with a different color from the leftmost house itself. We calculate this distance and store it as distance 1. Next, we perform a similar scan starting from the rightmost house, looking for the farthest house with a different color from the rightmost house. This distance is stored as distance 2. Finally, the result is the larger of these two distances, max, distance 1, distance 2. The advantage of this method lies in its simplicity and efficiency. Since we only perform 2 linear scans, the time complexity is O(n). Additionally, the space complexity remains O(1), as no extra data structures are used. This approach works because the maximum distance is determined by the endpoints of the array, meaning we do not need to check every possible pair. By reducing the problem to these linear scans, we achieve both elegance and speed in our solution. Given the advantages of the optimized approach, it is the clear choice for this problem. Compared to the brute force method, which has a time complexity of O(n squared), the optimized solution is significantly more efficient, running in O(n). This makes it not only faster but also scalable for large inputs. While the brute force method is conceptually simple, it is impractical due to the high computational cost for larger arrays. The optimized approach, on the other hand, directly leverages the problem structure, focusing on the endpoints and their relevant distances. This makes it both elegant and highly efficient. The main trade-off is that the optimized solution requires recognizing the key observation about the endpoints, which may not be immediately obvious to everyone. However, once understood, it becomes clear that this is the best approach to solve the problem. In conclusion, the optimized O(n) solution provides the right balance of correctness, efficiency, and scalability, making it the most suitable strategy for this challenge. In this problem, we need to determine the maximum distance between two houses in an array, where the colors of these two houses are different. The input is an array called colors, where each element represents the color of a house. The goal is to find two indices I and j, such that colors I is not equal to colors j, and the distance ji is maximized. To start with a brute force approach, we analyze the input array and use 2 nested loops to examine all possible pairs of indices I, j. The outer loop iterates through all starting indices I, while the inner loop checks all ending indices j that come after I. For each pair, we check whether their colors are different. If they are, we calculate the distance ji and compare it with the current maximum distance to see if it's larger. To keep track of the maximum distance, we introduce a variable max_distance, which starts at 0. Every time we find a new pair of indices with different colors, we calculate their distance and update max_distance if the new distance is greater. After evaluating all possible pairs, the algorithm returns the largest distance found. However, while this brute force approach works, it becomes inefficient as the size of the array increases. For instance, if the array has a length of 10 to the power of 5, the O(n squared) complexity from the nested loops leads to an excessive number of comparisons. To address this inefficiency, we turn to an optimized solution using the two-pointer technique, which reduces the time complexity to O(n). This method starts by initializing 2 pointers, left at the beginning of the array and right at the end. With the two-pointer approach, the first step is to check the colors at the 2 extreme ends of the array, colors left and colors right. If these 2 colors are different, then the distance between them, right-left, is the largest possible distance since the pointers are positioned as far apart as possible. In such a case, we can return the result immediately without further processing. However, if the colors are the same, we need to adjust the pointers to explore other potential pairs. Depending on the situation, we either move the left pointer 1 step to the right or the right pointer 1 step to the left, effectively narrowing the range. This adjustment continues until we find 2 houses with different colors, ensuring that the distance is maximized as soon as a valid pair is identified. The two-pointer technique works so efficiently because it starts by maximizing the potential distance and eliminates unnecessary comparisons. When we find colors left and colors right to be different, we know that no other pair can have a greater distance since the pointers begin at the extremes. This eliminates the need to check other pairs, drastically reducing redundancy. Additionally, the algorithm accounts for edge cases. For example, if all houses have the same color, there's no valid pair, so the result is 0. If the array length is only 2, the result depends on whether the two houses have different colors. For large arrays with repeated colors, this approach efficiently skips over irrelevant comparisons, ensuring that we only focus on meaningful checks. This problem is straightforward in terms of the data structures required. The input array colors is directly traversed using the two pointers, and no auxiliary data structures are necessary. The key variables include the left and right pointers, which track the indices being compared, and an optional max_distance variable in the brute force approach. From a complexity perspective, the brute force solution has a time complexity of O(n²), as it examines all possible pairs. In contrast, the two-pointer technique operates in O(n) time, since each element is processed at most twice. Space complexity for both approaches is O(1), as no extra memory is used beyond the variables required for computation. This makes the optimized solution not only faster but also highly memory efficient. This solution finds the maximum distance between two houses with different colors in the most efficient way. The key insight is that the maximum distance will always involve one house at either the start or the end of the array, since the farthest houses produce the largest distance. Let's break down the code. 1. Initialization. We start by determining the length of the input array colors and initializing max_dist to 0. This variable will hold the maximum distance we calculate. 2. First loop. We iterate backward from the last house to the first house, comparing every house's color with the color of the first house, colors, 0. If a house with a different color is found, we calculate the distance J0 and update max_dist if this distance is larger than the current value. Once we find such a house, we break the loop because we are guaranteed no farther house has a different color. 3. Second loop. Similarly, we iterate forward from the first house to the last house, comparing every house's color with the color of the last house, colors, n1. If a house with a different color is found, we calculate the distance n1 and update max_dist accordingly. Again, we break the loop once we find a valid house, since no closer house can have a larger distance. 4. Return result. Finally, we return the value of max_dist, which holds the maximum distance between two houses with different colors. This approach ensures efficiency because we only traverse the array twice, resulting in an O(n) time complexity. The solution also handles all edge cases, such as arrays where all houses have the same color, in which case the problem guarantees no valid input, or when the array length is minimal, n=2. This is the Java implementation of LeetCode problem number 2078, two furthest houses with different colors. The logic is directly translated from the provided Python solution. The Java version includes type declarations for the input array and uses Java-specific methods like math.max for comparisons. The structure follows a typical Java class with a method maxDistance which calculates the maximum distance between two houses with different colors. The approach iterates over the array from both ends to find the maximum distance efficiently. We start with example 1, where the input array is 1, 1, 1, 6, 1, 1, 1. First, we initialize two variables, n, which is the length of the array, n equals 7, and max_dist, which is set to 0 to track the maximum distance between two houses with different colors. Next, we compare the color of the first house, located at index 0, with the colors of all houses starting from the last house and moving backward. We begin the loop with j=6 and check if colors 0 is not equal to colors 6. Since both are 1, this condition is false, so we move to the next house by decrementing j. This process continues until we reach index 3, where colors 0 is 1 and colors 3 is 6. Here, the condition is true, so we calculate the distance as 3, 0, which equals 3. We update max_dist to 3 and break the loop since we've found the furthest house from the first house with a different color. Now, we compare the color of the last house, located at index 6, with the colors of all houses starting from the first house and moving forward. We begin the loop with i=0 and check if colors 6 is not equal to colors 0. Again, both are 1, so the condition is false, and we move to the next house by incrementing I. This continues until we reach index 3, where colors 6 is 1 and colors 3 is 6. The condition is true here, so we calculate the distance as 6, 3, which equals 3. Since max_dist is already 3, it remains unchanged. We then break the loop as we found the furthest house from the last house with a different color. The final output for this example is max_dist equals 3. In example 2, the input array is 1, 8, 3, 8, 3, 8, 1. We start by initializing n to 7 and max_dist to 0. First, we compare the color of the first house, located at index 0, with the colors of all houses starting from the last house and moving backward. Beginning the loop at j equals 6, we check if colors 0 is not equal to colors 6. Both are 1, so the condition is false, and we decrement j. At index 5, colors 0 is 1 and colors 5 is 8, which satisfies the condition. We calculate the distance as 5, 0, which equals 5, and update max_dist to 5. The loop is then broken. Next, we compare the color of the last house, located at index 6, with the colors of all houses starting from the first house and moving forward. Starting the loop with I equals 0, we again find that colors 6 equals colors 0, so the condition is false. We increment I until reaching index 1, where colors 6 is 1 and colors 1 is 8. The condition is true, so we calculate the distance as 6, 1, which equals 5. Since max_dist is already 5, it remains unchanged. The final output for this example is max_dist equals 5. In example 3, the input array is 4, 4, 4, 4, 4, 4, 4. We initialize n to 7 and max_dist to 0. Starting with the first house at index 0, we compare its color with the colors of all houses from the last house moving backward. For every j from 6 to 0, colors 0 is equal to colors j, since all houses have the same color 4. Therefore, the condition is false for all comparisons, and the loop completes without updating max_dist. Similarly, we compare the color of the last house at index 6 with the colors of all houses from the first house moving forward. For every I from 0 to 6, colors 6 is equal to colors I, so the condition remains false throughout. Again, max_dist is not updated. Since there are no houses with different colors, the maximum distance remains 0. The final output for this example is max_dist equals 0. To analyze the time complexity of our solution, we start by breaking it into two main loops. The first loop begins at the end of the array and iterates backward until it encounters a house with a different color from the first house. In the worst-case scenario, when all houses have the same color, this loop will go through every single element in the array of size n. However, as soon as a house with a different color is found, the loop stops early, meaning the number of iterations is at most n. Similarly, the second loop starts at the beginning of the array and moves forward until it finds a house with a color different from the last house. Like the first loop, it also stops as soon as a valid house is found, but in the worst case, it might need to iterate through the entire array. Each loop, therefore, has a time complexity of O(n). Since these loops run sequentially, the total time complexity of the solution is O(n) plus O(n), which simplifies to O(n). Now let's discuss the space complexity of the solution. The storage requirements are primarily determined by the input and any additional variables used. The input array colors is passed to the function, but since no extra memory is allocated for storing it, this is considered O(1) in terms of space. Beyond that, the algorithm uses a few integer variables, such as n, max_dist, j, and I, to store intermediate values. These variables require constant memory and do not depend on the size of the input array, making their space usage O(1). Since the solution avoids using additional data structures or recursive calls, the overall space complexity remains O(1). Let's compare the efficiency of the optimized approach with a brute force method. In the brute force approach, we would check every possible pair of houses to determine the maximum distance between two houses with different colors. This would require two nested loops, where the outer loop iterates over all n houses, and the inner loop examines all houses to the right of the current house. This results in a time complexity of O(n)².
However, like the optimized method, the brute force approach uses no additional memory, so its space complexity is O(1).
On the other hand, the current solution avoids the inefficiency of nested loops by focusing on two specific cases: the furthest house with a different color from the first house and the furthest house with a different color from the last house. This drastically reduces the number of comparisons, making the time complexity O(n), while still maintaining the minimal space complexity of O(1).
Finally, let's analyze the solution under different scenarios.
In the best case, where the first and last houses already have different colors, both loops terminate after a single iteration, giving us a time complexity of O(1). In an average case, the loops will terminate early after scanning part of the array, resulting in a time complexity of O(n). In the worst case, where all houses are the same color, each loop will iterate through the entire array, making the time complexity O(n). To mathematically confirm the big O notation, note that each loop runs at most n iterations, and since they execute one after the other, the total number of iterations is at most 2n. This simplifies to O(n), consistent with our earlier analysis. The space complexity remains O(1) throughout since memory usage does not depend on the size of the input. One of the most common mistakes when solving this problem is overlooking edge cases.
For example, not considering what happens if the input array is empty or contains only one house.
These scenarios can lead to runtime errors or incorrect results, so it's important to include preliminary checks, like verifying if the number of houses is less than 2. Another frequent issue is using inefficient nested loops to solve the problem. While this might seem straightforward, it results in O(n) squared time complexity for large inputs, which is impractical when n is significantly large, such as 10,000. Instead, you should aim to optimize with techniques like hash maps or sliding windows to eliminate redundant calculations. Additionally, errors in index bounds, such as iterating over indices without ensuring that the first index is less than the second, can cause logical issues or runtime exceptions. Always write loop bounds carefully and test your solution with small arrays to catch these errors early.
Lastly, misinterpreting the problem statement is another pitfall.
For instance, assuming that colors are unique or that the houses are sorted by color can lead to invalid solutions. To avoid this, carefully read the problem description and clarify any uncertainties if you're in an interview setting.
Another key area to watch out for is space complexity.
Using extra memory unnecessarily, such as storing all possible pairs of indices, can be inefficient when a simpler solution exists. For large inputs, minimizing auxiliary space is critical, so always evaluate whether your approach uses memory efficiently. When in an interview, it's often helpful to start with a brute force solution to establish a baseline understanding of the problem. Then, quickly transition to discussing optimizations to show your ability to improve efficiency. Look for patterns in the problem, like opportunities to use hashing, sliding windows, or sorting, to simplify your approach. It's also important to articulate how you handle edge cases, as this is a common area of focus for interviewers. Be ready to discuss the scalability of your solution, especially for inputs near the upper constraint limits, and explain the trade-offs between time and space complexity. This will demonstrate not only your problem-solving skills but also your ability to think critically about real-world constraints. This problem shares similarities with several related problems on LeetCode, which can help you build the right intuition. For instance, in LeetCode 1, the two-sum problem, a hash map is used to efficiently find two numbers that add up to a target. This teaches the value of avoiding nested loops by leveraging auxiliary data structures. Another example is LeetCode 15, the three-sum problem, where you need to find triplets that satisfy specific conditions. It requires careful handling of edge cases and duplicates, which is a transferable skill. Sliding window techniques are also highly relevant. For instance, LeetCode 567, permutation in string, uses this approach to check if a string contains a permutation of another. Similarly, LeetCode 438, find all anagrams in a string, employs a sliding window to efficiently match patterns in a string. These problems highlight techniques like hashing and efficient traversal, which are crucial when tackling the two furthest houses with different colors problem. There are several alternative approaches to solving this problem, each with its own trade-offs. The hash map approach involves storing the last seen index of each color, allowing you to find the furthest houses in O(n) time complexity. While this is fast, it does require extra space, which may not be ideal for memory-constrained environments. Another method is the sorting approach, where you sort the houses by their colors and then compare adjacent houses. This reduces the complexity to log n, but modifies the input array, which can be a drawback if the original order needs to be preserved. Finally, the sliding window approach uses 2 pointers to identify valid pairs in a single traversal. This method can achieve time complexity without additional memory overhead, but it may require extra logic to handle specific constraints or edge cases. Each of these techniques offers a balance of trade-offs, and the best choice depends on the problem's requirements and constraints. Great work! We've covered the brute force approach and discussed the key insights for solving this problem. Remember, starting simple and optimizing is a valuable skill in problem solving. Don't forget to practice regularly and stay curious. Thanks for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!